Okay, we are on YouTube. And now I'm going to post this on our channels. Okay, we are on YouTube. Okay. Okay, I'm going to start broadcasting now. So we're going live. Everybody's ready?
Yes, sir.
Yes, sir.
Yep.
We're now broadcasting to all attendees.
So we'll be starting at 1 p.m. Eastern, right?
Correct.
Okay. Okay, I have 1 p.m. Eastern Time. Welcome to Cutting Edge Digital Manufacturing Part 1. I am John Hornick. I'm the Chief Strategy and Communications Officer for Nscript, Inc., and I'm also author of the book 3D Printing Will Rock the World. This is part 1 of a 2-part webinar. Part 2 will be the same bat time and the same bat channel on Tuesday, July 7th. I might have just dated myself by saying it that way. Thanks everyone for signing up. We hope everyone is safe and healthy. We're excited to get a great turnout today. Just a couple of ground rules. We're going to take all questions at the end. Each speaker is going to have 15 minutes, and LJ Holmes and I will give them a 2-minute warning and a time's up warning. We should have about 30 minutes left at the end for questions. All questions are going to be in the Q&A feature on the Zoom platform. The audience is going to be muted even during the Q&A session. Please address your questions to any speaker that you like, or you can just address them to the whole panel. So now my colleague, LJ Holmes, will introduce the first speaker. Hope you enjoy the webinar.
Thanks a lot, John. I appreciate that. And thanks everyone for joining us. We're going to have we've got a great lineup today. Our first speaker is Dr. Mark Morosnick from the University of Delaware. He's a professor in electrical and computer engineering. He's also recently taken on the chair of that department. He and his team are absolutely world leaders in the area of multi-material, multi-technology, additive manufacturing for electronics, and with a huge emphasis in next generation communication and RF devices. He's got some great stuff, and I'm excited to hear about it. So it's my pleasure to introduce my friend and colleague, Dr. Mark Morosnick.
Great. Thank you so much, LJ. And I appreciate Nscript for inviting me to give this talk. So let me share my screen. And, all right. Can you give me the thumbs up? Can you see the slides okay? All right, terrific. Great. So I appreciate that, LJ. I'm Mark Morosnick. I'm a professor at the University of Delaware, and my group works on the use of additive manufacturing, particularly multi-material, multi-tool additive manufacturing for functional devices, printed electronics, sensing, and I'm happy to talk about some of the stuff that we're doing at the university. So here's a quick outline of my slides. I'm going to try to motivate the subject a little bit by answering the question why, which I think is a perfectly reasonable question to ask. Talk about some of the core challenges that we face, and then I'm going to give some application areas that we're working on at the University of Delaware. So the why question I think is perfectly valid, especially when it comes to printed electronics. If there's one thing we're really good at, it's manufacturing low-cost circuit boards at extremely high volumes, and it's unlikely that additive manufacturing is going to be able to meet the volume or the cost of traditional circuit board manufacturing. But there are a number of niche areas where additive manufacturing has a large role to play. Some of the most obvious, point of need manufacturing. So here's where you need replacement parts that aren't easy to get on the space station, at forward operating bases. So it'd be great to have a printer that could actually generate new printed circuit boards whenever you needed them. There's applications for small volume, labor intensive parts. We've done projects for companies that made really complicated antenna assemblies that took hundreds of man hours to be able to complete one, and they only made hundreds a year. You could replace some of that manufacturing with additive manufacturing and cut costs. But I'm an academic, so the reason I'm interested in this is really to build things that there's no other way to do. And there's a number of examples of those. I stole this image on the left from Professor Rumpf, who's going to talk to you in just a minute, because he's doing truly remarkable work on 3D electronics, being able to place non-planar circuits any direction you want. We've done quite a bit of work on complex three-dimensional geometries that are no way you could manufacture other ways. The image there shows an antenna. This is a very, very tiny high-frequency antenna, but if you dug in the inside, you'd find this has multiple conductive fins that aren't touching and have spatial resolutions of 25 to 50 microns. Very, very difficult to envision how we'd make that any other way. Another example, and this is not an exhaustive list, but another example is the ability to make spatially graded or spatially varying material properties. So nobody's really investigated this much because there was no way to really fabricate it. But there's lots of applications where you can create interesting electronics and electromagnetic devices by being able to grade material properties in any arbitrary way. There are some challenges to get there. So the state of the art, where is it? Well, I think if you looked at it 10 years ago, it'd be closer to the image on the right. 3D printing and electronics was making boxes that you'd put other devices inside. We're beyond that. We're not at the image at the left, where we're making fully conformal touchscreen electronic devices. And so the state of the art is somewhere in between. And hopefully with some of the projects you'll see myself and some of my colleagues working on, you'll get a sense of where we are. Before I go into those projects, let me talk about some of the challenges that I see going forward. And there are quite a few. And I'm going to talk about 4 of them. Materials, software, monitoring and control, and new additive manufacturing or multi-material additive manufacturing systems. I think materials is probably the biggest issue we now face, especially in the kind of work I do in functional electromagnetic applications. Simply a lack of commercially available materials that I can use in those devices. We're looking for materials that we can print that have high electrical conductivities that approach bulk metal properties. Particularly at the frequencies we're interested in, at the high frequencies, most of the inks and pastes that we purchase and can print are as small as an order of magnitude below bulk metal properties. And for many applications, that limits the frequencies that we can actually use this technology for. We're looking for printable thermoplastics, resins, and inks with a range of electric and magnetic properties, high permittivities, low permittivities, magnetic properties. And we're even looking for a range of materials that are active materials, temperature sensing, piezo, electric or piezo resistive. And I'll talk about some of the materials that we're working on at the University of Delaware, but I think this is a huge bottleneck in the technology that we have to work on. Another big challenge is the software, and I'm not going to talk about this too much because Professor Rumpf is really the expert on this. Developing novel software that's suited for multi-material, multi-tool additive manufacturing, that doesn't exist. Most circuit board analysis and layout programs are designed for single or multi-layer planar boards, single substrate, right? But if we're trying to make conformal or pure 3-dimensional structures, that software is inadequate. Moreover, all the additive manufacturing systems that we use to build these, the multi-material, multi-tool, combine multiple manufacturing tools on the same platform. So the software has to be able to seamlessly integrate all those tools together to build the device. And the last question is, how do we go from what's currently done? We call it 3D printing, but it's really 2.5D, layer by layer, to true 3-dimensional printing. So software is a big challenge that I think Professor Rumpf has made a large advances on. Another big challenge is really closed loop monitoring and control. Anybody who's done much additive manufacturing can sympathize with the picture in the middle of the screen. This is FDM printhead that we walked into in the lab one Monday morning, and it's not the first or the last that that's happened. The problem is that all of the AM systems I know of are almost entirely open loop. They simply follow the directions, and if something goes wrong, they continue to operate as if the part is working. There is a critical need for us to be able to do process monitoring to at least identify when a problem occurs and maybe stop the print process, but better yet, come up with control features that can identify problems and be able to rectify them during a print process. I think that's absolutely critical for us to be able to match the quality and consistency of conventional manufacturing. I think of all the applications you're going to see me show today, and probably most of my colleagues, there's boxes of failed prints that happen before and after the one I'm going to show you. It's very difficult in these things to get consistent results when there's no process monitoring or control. And the last thing I'll talk about is the systems. Most people who do electronic 3D printing actually combine a number of 3D printers together, either through some manual assembly or they move the part manually. So they'll print polymers using FDM, then they'll move it to another machine and put some metal on there, and then they'll either pick and place or manually manually insert components into it. So this results in really long fabrication times and lots of failures due to registration errors. With the spatial distances we're trying to reach, it's not practical to move the part from one machine to another. Moreover, for some of the more complex 3D electronic designs that we've worked on and Professor Rumps has worked on, it's impossible to make these structures without having an integrated approach. So what we're really interested at the University of Delaware is this Swiss Army knife approach to additive manufacturing, a single machine that combines a multitude of different printing modalities and materials without having to move the part. So I admit I do not work for Enscript, but I'll put a plug in. We are big fans at the University of Delaware, and mostly because they have what's closest to the Swiss Army knife approach to additive manufacturing. Their systems allow us on a single, very high resolution stage to put a variety of printing modalities and materials together. So at the university, we have currently 2 3D printers, the 300 and the tabletop. And we're getting our 3rd printer at the end of, or towards next month, which will be a 6-axis that I'll talk about, and a host of gizmos that we can print with, some of which we've purchased from Enscript, some of which we've actually made custom and integrated into the system. So for those of you who've never used an Enscript, there's a variety of things you can do with it. The smart pump technology that you can see on the top can print virtually any ink or paste. We make all of our custom materials of a range of viscosities, and we've printed modeling clay to water out of these things at very high resolution. So this allows us to do a lot of work in material development of new materials and print those as custom inks and pastes. It has a very nice FDM printer for doing thermoplastics, pick and place of electronic devices. We have a micro mill, which is really useful for RF devices because many of the surfaces are too rough after we FDM print them at the high frequency. So we go over those surfaces with a micro mill and can smooth them down to a couple of microns, and that makes a huge difference. And we have some custom heads that we've integrated. We developed our own hopper-fed FDM system. So instead of having to make filament, we can feed pellets, which are highly loaded, in many cases with ceramics or magnetic particles, and it extrudes and prints directly. So you never have to make a filament, and we can print that directly through the Enscript. We've also integrated a 3rd-party head, a nanojet aerosol print head for aerosol jetting of particularly conductive inks. The print head's made by IDS, and it was easily integrated within the Enscript platform. So this is a range of gizmos that we're able to use. This is the one that's coming. So this is what we're really excited about, to get away from XYZ printing and go to true 3-dimensional printing. So this Enscript is coming next month, and we'll be able to do true 3D printing through a 6-axis. So pitch yaw, rotate part, XYZ, all the same gizmos through a tool changer. So we're super excited about being able to explore that. A little bit of a talk about the laboratory I have at the University of Delaware. So we have a brand new laboratory, 4,500 square foot lab dedicated towards research and applications of functional additive manufacturing. And this is where we house all the Enscripts, all our material development, and a variety of other printers. I talked a little bit about materials being the bottleneck. So I'm not a material scientist, and I kind of got pulled into that kicking and screaming a little bit, but it's absolutely essential to do the kind of things that I want to do. And so we do quite a bit of functional material development at the University of Delaware. We have our own custom, we can make our own custom made polymer filaments for FDM. In this case, these are filaments that we put additives in to change them, their electromagnetic properties. So we can make high dielectric constant, low dielectric constant, magnetic, temperature sensing. We've made a range of polymer filaments that we can spool and print using FDM. We also make a lot of functional inks and pastes that we can print with the smart pump technology. So we've made our own highly conductive inks, magnetic inks. We have a resistive ink that we use for chemical sensing, and we're starting to print batteries. So I'm going to jump into some of the application areas that we've worked on to give you a sense of where we think the state of the art is. The bread and butter for most of the work that I do is really high frequency RF applications. And we've made RF devices that have worked all the way from DC to 110 gigahertz. Here's some examples. The one on the left is a RF printed assembly. This was a military project to see if you could 3D print the front end of a KU band communication or radar system. And so everything you see there was either printed or pick and place, with the exception of the connectors, which were put on at the end. Everything else was printed or pick and place, and it functioned. The goal of this project down the road is to make this entirely conformal, so we'd have an RF front end that we could fit into a cone shape or a spherical shape.
And Mark, you got about 2.5 minutes left.
Okay, then I'll go fast. So then we've done a lot of printed antenna stuff and connector work. Here shows an example putting it all together. So this is an antenna. I don't think there's any way to make any without additive manufacturing. It's a dual band, dual polarization antenna, has 2 different permittivities and all printed connectors. These are SMA connectors that are threaded that we print on the structure. The connectors are by far the least sexy, but the most useful part of the device and the point of large failures. This shows us printing a chemical sensor. So this was used to try to, on a flexible substrate, and it shows the end script being able to print all of the electrodes. We had a chemi-resistant ink that we put on there, and we could pick and place all of the electronic gadgets. At the end, all we did is put a battery on there and it worked. We've integrated that chemical sensor actually for an Army project into the shape of a 40mm grenade ammunition. The idea here is we have a chemical sensor into this form factor that soldiers can carry with them. They already carry these 40mm grenades. Instead of taking the normal grenade, they would take the chemical sensor, launch it into an area they're interested. It will wirelessly transmit chemical data back. This is the last one. I'll stop at this. So the last project, kind of a fun one, printed robotics. So the idea is, can we print a fully functional robotic system that when it walks out of the printer, pushes the button and prints the next robot? So we're not quite there, but this shows our what progress we've made over the last year. And so the idea is everything is going to be printed or pick and place. We're not quite there yet. And it'll be removed automatically from the build plate, can move off the build plate, survive a fall, and then you can make the next one. So this is a fun project we're working on with Tardec on seeing whether we can do. So this shows it being snapped off the build plate. And I'll end when you can see it falling off the table. So it had to survive a fall off the table onto hard ground, and pretty soon you'll see it scatter on the ground there. There it goes. So that's about the closest we got to an automated 3D printed robot. Hopefully if we do this next year, I can show you advances on this. So I'm gonna stop there. We've done work on printed ceramics, high temperature applications, so if anybody has any interest there. And we've done a lot of work on passive beam forming lenses for antenna work. So I think I will end there, and I'll take questions at the end.
Thanks a lot, Mark. I appreciate it. John?
John, you're on mute.
Unmute. Nope. Okay.
You're on mute again, sorry.
Mute. Okay. Can you hear me now?
Yeah.
Okay, good. Mark, impressive work. I have the pleasure of introducing Dr. Jing Wang, who's professor of electrical engineering at the University of South Florida. Dr. Wang is a co-director of the Center for Wireless and Microwave Information Systems in the Department of Electrical Engineering. He's a recipient of the 2018 Faculty Outstanding Research Achievement Award at the university and the 2017-18 Outstanding Electrical Engineer Educator Award. He holds dual BS degrees in electrical and mechanical engineering. He also holds 2 MS degrees in electrical and mechanical engineering and electrical engineering, and he has a PhD in electrical engineering. And he worked on this in collaboration on this presentation with Dr. Tom Weller at Oregon State University. Dr. Weller joined Oregon State in 2018 as a professor and head of the School of Electrical Engineering and Computer Science. And Dr. Weller's research focuses on microwave circuits and antennas, including an emphasis on additive manufacturing. Dr. Wang is going to speak on additive manufactured and 3D dielectric-enabled RF and millimeter wave devices and systems. So, Dr. Wang.
Thank you. Let me show the slides. Sure. Can everybody see the slides?
Yep.
Okay, I'll start. Thanks for the introduction. As my title suggests, today I will talk about 3D printed dielectric-enabled RF and microwave device and microwave system applications. Let me move to the next page. Mark already did a very good job of talking about general background introduction about why there's a need for integrating electronics together. So I will skip some of those details, only to say, referring to this picture for Pope gathering happened in 2005 and 2013. The big jump back then was driven by the mobile phone, smartphone, and there's a need for gadget. Everybody having one back then. Now you may have multiple, attending any sort of events. Unfortunately, this year is the year we have this pandemic, so everybody go virtual. That's also driven things like wearable electronic sensors, particularly targeting for personal health reasons. So there's a need for packaging different level of complexity electronics for RF all the way to millimeter wave circuit, particularly targeted for 5G. Let me move down. So what triggered me to get interest in this kind of project was the early NSF-funded effort between collaboration between USF and Vermont and Stanford Research Institute. At the time, we tried to build a 3D sensor that has a 3D integrated antenna. Such a sensor should be battery-free, totally passive, receiving a fundamental interrogation signal at the time at 2.4 gigahertz, sending back double frequency output at 4.8. We're applying the sensor modulation on top of it. At the time, we choose to work with a piezoelectric commercially available sensor that generate a waveform based on the vibration. We're gonna detect the waveform at the receiver side wirelessly using the sensor. The key idea is to keep the antenna radiation pattern controlled to be unidirectional, and also keeping the antenna gain and efficiency maximized. We're using a decent matched input and output to keep the conversion efficiency high. So the sensor we developed showed a very high conversion efficiency, which is negative 10 dB. Every signal coming in at the fundamental signal, about 10% of the signal strength coming out of the double frequency, which was the record at the time. With that, we can deliver the sensor with the remote sensing with a distance about 30-some meters, which was the length of the roof of our building. So in order to do additive manufacturing, we picked to work with the technology offered by Nscript, and which is combine laser machining with additive machining together in a single platform without moving your part off the printer bed. And we started with printing multiple layer in a way, multiple material, alternating printed substrate material, printed conductive material in a way very similar to how the traditional printed circuit board, multi-layer board is constructed. We're doing so by adding some of the features such as electronics, either manually embedded or pick and place embedded into other important RF components, such as the feeding network for antennas, antenna themselves, and some other combiner and splitter of the power and filter functions. With added laser machining, we're able to achieve feature size down to about 3 to 5 microns, as are detailed in some of the later part of the discussion. And we also play with the wavelengths of the laser to enable the feature size to be a certain range. As you can see in this picture, also by using laser, you cure the center, you center and cure the ink at particular locations, which also help you to reduce the losses of the conductive ink. So this is an early example that we have collaborated with Pure Nscript. There's a YouTube video you can find to build the unit cell of this 2.45 gigahertz space array, which has the unprint filter miniaturized because of the integration of capacitor, but also having a differential feed network, have antenna, have all these other phase shifter components integrated. In all the different phase shifting state, It shows a good impedance match in the frequency of interest 2.45 gigahertz. And this is a radiation pattern. Eventually, we built it into a quadcopter collaborating with Superior Enscript to assemble 4 of this unique cell into a bigger array. So carry on the previous work, we try to simplify the layer structure, fully modifying the layer material properties, such as making some of the layer with low infill ratio, targeting for achieving better radiation performance, particularly wider bandwidth, better front-to-back ratio by inserting a cavity on the back of a patch antenna and feeding the patch antenna using aperture. And also one of the key elements we already have in the previous example, in this case, we try to introduce a conformal low form factor, hopefully totally flat insertion of microelectronics. At this stage, we're still dealing with packaged electronics, such as phase shifters, switches, and other electronics, all combined into a multi-layer print. The previous example have 7 conductive layer, 7 substrate layer. Most of these print have fewer layers to further simplify the print, improving the yield and also reducing the time. So the next page is an example of this print. So we designed such an X-band phase array, and this phase array shows this 5 conductive layer and 6 substrate layer. Most importantly, in order to improve the antenna radiation pattern, we introduced 50% infill ratio, reduced dielectric on the back of the patch antenna. And also we inserted this cavity to modify the front-to-back radiation pattern. And we directly inserted the phase shifter chip in a QFN package, while directly printing on top, making the cavity, so using isolated weir hole pillars. By implementing all this measure, we achieve fully printed phase shifter package. And we are able to engineer the back lobe, as I will show you in the next page, and the front-to-back ratio. And we're able to tolerate different type of antenna design and feeding network. In this case, we're using aperture to feed it, but we could also change it to other configuration as well. So there's 4 layers of printed ink and 5 layers of ABS substrate in this multi-layer print. So here shows the electronic measure performance of such a phase array. As listed here to the left, this phase array shows about 24% of bandwidth. As you can see, all the bits showing a good reflection coefficient between 9 and 11 gigahertz, which is the operational band of such a device. And we achieve a radiation gain. The peakest gain is 7.2 dBi, with 6 dBi of gain between 9 and 11 gigahertz. And this device shows radiation efficiency of 80%. While including all the transition features we incorporated into the print, and showing a front-to-back ratio better than 20 dB. Most interestingly is this plot, which shows all the bit of the different bit of the phase shifter. As you can see, they're more or less flat across the operational band. So since I'm not showing this in a slide showing modes, this movie will not play. This would be a movie showing how we print the cavity on the top to hermetically seal the already packaged IC underneath that. After sealing the IC, we also tested this package as a hermetic protection. Besides the electronic feeding on the side for DC and RF signal, this package we directly printed on top of the package also serve as a hermetic protection against the environment. So this briefly shows all the layers. One of the most important feature was to use laser machining to make a cavity. So when we pick and place or manually insert the IC die, which is about 50 to 100 micron in thickness, the IC can sit snapping and sit in the precise position and flat on the surface. We're in contact with a weir hole or ground contact on the back. On the front side, we also implemented, instead of using wire bonds, of course, we directly printed the interconnect to all the probe paths, which is in the 50 to 80 micron size range. In order to make a transition between a CPW probe feature into the microstrip, we're using the laser machining to enable that. which allows to do features down to back then 10 microns at a bigger wavelength, a longer wavelength. Let's switch one more page. There's always a delay for switching page. Anyway, I keep on jumping that page. This is an integration of two different IC dies together. One of them is the broadband distributed amplifier that we designed in the class I offer at the university. We tape out with Qorvo. And this is a circuit I will show performance in the previous package. In order to test this distributed amplifier, we compare the performance measured in a QFN package, wire bonding package, compared to direct print, as you see in these kind of figures. We also combine in a cascade configuration this broadband amplifier with a switchable, tunable filter that has two different states. As you can see in both of the state, filter and broadband amplifier operating with good reflection coefficient in the band, but also very minimal insertion loss cascaded with these two circuits together. Another important feature by using laser machining, we more precisely achieved the impedance characteristic impedance of the transmission line that otherwise was a little difficult to do. As you can see, the pink layer, pink response is based on direct print feature. The blue response is based on laser trim. With laser trimming, we're able to get a better reflection coefficient across the whole band. As a result of that, we also reduced insertion loss or the transmission loss of the interconnect features that we implemented in such a circuits. I jump another slide. So this is the last slide on the printed IC packaging due to the time allocation. So we eventually pushed towards a millimeter wave demonstration of such a technology, further simplify the layer structure, further simplify the transition needed, such as a weir hole, as you can see in this picture, and the CPW to microstrip configuration, and also all the DC feeding features to directly pick and place and print such a package in a more planar 2.5D kind of configuration. We tested the transmission line by themselves. As you can see, the attenuation dB per millimeter all the way up to 110 gigahertz has been characterized. We use different wavelengths of laser to train them, which have different layer of sintering effect. As a result of that, you can see the attenuation was a little different. In order to fulfill the feature to transition from the ground plane and other layers, we're heavily leveraging direct printed weir hole. As you can see, this is the picture. We're in the middle of printing the weir hole features. Eventually, we integrated this low noise amplifier with all the feed network, everything. We compare a directly measured probe response versus a package.
Dr. Wang, you have about 2 minutes.
Okay, so let me move to the next page. So the next topic, another important topic I can hopefully quickly cover in the 2 minutes time frame. So it's moving towards dielectric. This is driven by the fact that most of the conductor losses is still very high. When you talk about 100 gigahertz or 50 gigahertz and above, but as you go into the higher frequency, the wavelengths also shrink due to the use of sometimes high dielectric constant material. And there's the ability you can print those as if they're optical fiber. You can incorporate feature like total internal reflection using those fiber-like dielectric waveguide to be interconnect between chips and chips, sometimes between integrated circuit and modules. So we developed such a technology by using in-house developed material, the so-called composite. We can print both the dielectric waveguide. This particular design is going to be fitted to the metal waveguide feature. We measure different kind of contribution of losses, including dielectric loss, the total loss, the radiation-related losses across the range of frequency they operate. General rule of thumb is these type of devices have a potential to reduce the transmission loss by another order of magnitude compared to anything you can do with a planar transmission line. So as a result of that, we also further investigated such a feature with without a so-called cladding material to further increase the bandwidth, while also reducing the coupling to the adjacent features, allow the structure to bend one more slides I will show is for such a device with without cladding layer, which is a low-K dielectric enclosure. If I can switch slides. With the cladding, the bending of the dielectric waveguide, which is very critical for splitting the power, for feeding a very complicated antenna structures, doesn't introduce nearly as much effect due to the use of the cladding, that is low K enclosure to the high K core. We also tested such a dielectric waveguide up to 170 gigahertz using traditional waveguide as a feeding network. Of course, waveguide become cumbersome when you go to this kind of frequency range. The next a little bit topic we'll talk about is how to use the planar feeding network to feed such a device, which we started to research in the recent days. Somehow switching the page is slow. If I can go back one more page.
Yeah, Dr. Wang, unfortunately, I'm going to have to ask you to finish up pretty soon.
Okay, let me just go to the final slides. So we also use such a dielectric waveguide to build filters by integrating metallic pattern with the dielectric pattern. This is one page I want to show you. Instead of using metallic waveguide, in the future, you do want to have a connector-like feeding structure. This is one of our early approach to use the microstrip to feed it and then connectorize it to the external world. So you can then combine the dielectric-enabled transmission line antennas with traditional planar transmission line like structure into a system. With that, if I can move to one more page, that would be my conclusion. So we did demonstrate radiation antenna using the dielectric waveguide fed by the planar feeding structure we developed as a feeding structure. As you can see, with the enclosure of the dielectric cladding, most of the radiation pattern tend to be confined into the radiation direction. You're expecting a better gain, better radiation performance, a more pencil beam-like behavior, which you need in the 5G. With that, I will just quickly say our research focuses on a combination of different integration of electronics, but also a combination of introducing spatially engineered 3D printed dielectric to allow you to make some kind of unique radiation devices such as antennas. In order to do so, we also develop all the material in-house. With that, I will just conclude.
Thank you, Dr. Wang. Very good presentation. I now have the pleasure of introducing Dr. J. Devin McKenzie of the University of Washington. Dr. McKenzie is the Washington Research Foundation Professor of Clean Energy and an Associate Professor of Materials Science and Engineering and Mechanical Engineering at the University of Washington. He directs the Washington Clean Energy Test Beds, which are an open access laboratory and world-class printed electronics and energy fabrication and testing capabilities with 230 industrial and academic users. Devin has over 230 patents and publications that have been cited almost over 10,000 times, actually almost 10,000 times, and has a PhD, MS, and SB degrees. Devin is going to speak about 3D printed electronics and multi-materials integration for energy and health applications. Devin?
Great. So I'm going to talk to you a little bit about some of the work we do in the Washington Clean Energy Test Beds related to advanced manufacturing, where we really span the full range from early stage prototyping of devices all the way through to large format screen printing, all the way to full roll-to-roll fabrication of things like very large area energy devices, solar cells, and ultimately batteries. And a little bit about how Inscript work and the sort of additive 3D printing work fits into that puzzle. And I think we cover a broad range of applications. And an area, of course, in the top left is solar manufacturing, where we think about extremely large scale manufacturing. How do you make billions of square meters of devices much more cheaply than we can with silicon? But it also, we also span down to much smaller things, things where we start talking about on-body devices, human wellness devices, where actually the challenges are the same, although some of these devices are smaller relative to microelectronics. We're still talking about large area devices. And when we talk about large area devices and the human body, or large area devices and optimized transportation vehicles, you start to realize that the kind of paradigm of planar devices has its limitations. There's no part of the human body that is flat, and there's no part of the human body, external part of the human body, that's actually rigid. And putting rigid things in contact with flexible human bodies destined to failure. Putting rigid things in contact with surfaces in transportation are also problematic. Or we're starting to explore things like hypersonic vehicles, and how do we put electronics and sensors on the surface of hypersonic vehicles? Vehicles that are going to go from 20 degrees C to 1,000 degrees C within a single flight. So huge amount of thermal contraction and shape change involved. And of course, other energy devices like batteries, which might have to fit in any one of these categories. They might have to work on the human body. They might have to work on a hypersonic vehicle nose cone. And today since we had so much excellent presentations on things like RF and antennas, robotics and things of that sort, I kind of want to focus more on some of the specialty areas we work on related to embedded devices and multi-layer integration of functional materials, where, as I think our first speaker turned out, that materials is a major limitation in this space. And we use our Inscript, our 300 tool, not just as a conformal printing tool. We do some work in that, but actually through my experience in OLEDs and transistors and sensors, realized, and batteries, that it was a tool that allowed us to print just about anything. If we have a complex set of materials integrations, say a battery can be a 3 to 7 layer device of 7 different materials, all hetero integrated to each other. What's a system that we can actually do that with? And many times that answer is the Inscript system that we use. And so I'm going to talk on 2 areas, one in batteries, and then I'll talk about some wellness sensing, sort of special medical sensing devices where we need that really special materials capability, and how do we hetero integrate materials in a single manufacturing process. So batteries is, everyone needs batteries, whether we're trying to make Teslas, we're trying to make SpaceX satellites, we're trying to make Bluetooth headsets or IoT devices. Batteries is a ubiquitous need. We start thinking about, at the small end of that, thinking about IoT, smart labels, wireless, medical and pharmaceutical related devices. The batteries need to be extremely thin, and also other important characteristics. They have to have very low environmental impact. As we start seeing smart packaging, we start seeing, say, cold chain labels, electronic labels on your, your package of meat for the grocery store or from your pharmaceutical delivered via internet. You want to know that those foodstuffs or those drugs have been kept at the correct temperatures, or actually what they say they are brand protection. We're embedding electronics into those. We want those electronics to be sort of inconspicuous, embeddable, and the competition in that space is essentially the 3D printed barcode, which is incredibly inexpensive and very conformal, easy to use, but of course passive. We want to add active functionality to that, but we need to do it in a way that's very low environmental impact in terms of materials, because many of these devices will end up in a landfill. So lithium is out. Of course, lithium for transportation is also an issue, because lithium content in a transportation package can deem that to be a hazardous material shipment, which is also a big problem. So we're looking at new material systems that can be for batteries and energy storage, that can be ultra thin, can be low environmental impact, and ultimately scale to very large scale manufacture if we meet our goals here. And it's an interesting area of the spectrum. If you look on our right, this is energy density for cell thickness for different cell technologies, and most of the world is rightfully obsessed with sort of large format batteries that are centimeter scale batteries, batteries for electric vehicles. That's virtually every battery manufacturer in the world is trying to push in that area because of the sort of near-term potential for large-scale sales. But interestingly, when you take lithium polymer technologies, nickel metal hydride technologies, you start scaling them down to thinner and thinner cell thickness. And what's a target? A target for cell thickness for a thin battery might be a few hundred microns. Anything above a couple hundred microns is no longer essentially flexible, no longer conformal, because of the sort of shear stresses involved in a thick device as you make it conformal. Anything more than hundreds of microns will cause significant compressive and tensile strains and actually tear devices apart. It's very difficult to make flexible devices thicker than a few hundred microns. But if we look at like lithium polymer batteries, as they get thinner, to make them that thin, it is possible, but their energy density drops dramatically. We're just talking about 500 watt hours per liter, 500 milliwatt hours per cubic centimeter, whatever, however we want to term it, for lithium polymer. But when in lithium ion technologies, we start talking about lithium batteries for ultra thin applications, the energy density rolls off dramatically. So, and why is that? A lot of that has to do with the assembly and packaging of that device. Lithium is highly sensitive material to moisture and even nitrogen. And in order to package it, you need hundreds of microns of packaging, making it extraordinarily difficult to make a device thinner than a couple hundred microns of any significant capacity, because the packaging itself is thicker than that, even with no battery involved. So we look at other technologies, more sustainable things like zinc batteries. Worked with a company, Imprint Energy, which also used 3D printing dispensing tools to prototype batteries with their printed zinc polymer technology. Now at University of Washington, we're looking at metal air batteries as the ultimate thin film battery, an ultimate battery for things like food packaging and on-body applications, because they work warm and they work moist, and they actually don't require packaging. In fact, they're open air batteries, so we actually eliminate that need. So we've developed a material set. Getting a little bit slow advance here. We developed a material set to realize a fully printed, additively manufactured metal air battery system, where we use the 3D printing in planar structures, but to integrate complex materials, where we want to build monolithically integrate a battery. We can't use a separator and packaging assembly cell like a pouch cell, lithium pouch cell that's held together by atmospheric pressure. We need to make a monolithically integrated battery that each layer is in electrochemical contact or electrical contact with the other layer inherently, and requires no further assembly. So we develop custom conductive inks, of course, to conduct electricity, but anode inks, in this case, zinc metal inks, with conductive additives to provide our zinc ions for our zinc batteries. We need to develop electrolytes, and probably this is the trickiest part. We develop a polymer, ionic liquid, deep eutectic solvent-based electrolytes that print as liquids, but then hold a solid shape so that we can then print on top of them, which is a fundamental. Not only can we print on top of them, they need to hold their shape to print on top of them, but they also need to hold their shape in the final application. There's no other separator here. There's no mechanical structure that can hold the anode and cathode from shorting into each other, except for this electrolyte. So it has to be a semi-solid electrolyte. So we develop these materials that can be printed and then formed into semi-solid or solid flexible materials. And then on top of that, we develop sort of custom nanomaterials for our air cathode that does the air reaction, the oxygen evolution, oxidation reduction reactions necessary for an air battery in contact with the air. And that's a really complicated multifunctional hierarchical material where you have to catalyze the cracking of air, cracking of oxygen, to form OH ions into our air battery. But we also have to bring so that material has to be in contact with the air. It also has to be in contact with the electrolyte, and it also has to be in contact with an electron source or sink, because we have to bring liquid, or we have to bring electrolyte in to conduct ions in contact at the same triple point with air coming in and with electrons, so that we can get electrical current out at the same time. And we developed that with a graphene-based sort of nano-decorated graphene-based catalyst, which is on conductive graphene, with a multi-wall carbon nanotube network that's porous, that allows electrical conduction out of the network, but allows gas penetration. And then on top of that, we'll for example, inscript print a current collector, a sort of grid-like current collector, to actually pull and collect the large currents to pull them out of the battery. This is sort of an example of a cross section. As far as we know, this is the thinnest battery, sort of thinnest printed battery or flexible battery of its kind in the world. We see a structure of an anode, a solid printed electrolyte, and this hierarchical catalyst. And we demonstrated that out to by developing those materials, really optimizing the electrochemical performance, but also the electrical performance, to get to high rate pulsing, something notoriously difficult for metal air batteries. You use batteries, metal air batteries in hearing aids. Now you stuff it in your ear, it's warm and moist, works great. But those are actually very low current. Those might be 10C to 50C batteries, which are, sorry, 150, 1 over 50, 1 over 10, 1 to 1 over 50C batteries, in the sense that they dissipate their capacity over, 20 to 50 hours. That's actually a very low rate. They're typically very hard to get those to pulse. If we want to use those things for like wireless sensors, for really almost any electronics now, ultra low power electronics, where they're primarily in a sleep state and then are woken and activated to send out or receive a wireless packet, for example, they need to have instantaneously very high current. For this size of battery, anything from a few milliamps for very low power BTLE up to 100 milliamp sort of pulses for, say, a LoRa sort of long distance wireless signal. And we've actually, because of this structure, this very thin integrated structure, we've been able to demonstrate this sort of multi-milliamp, maybe 5 milliamp per square centimeter or more pulsing out of 100 micron total thickness battery. And that's everything. That's substrate to top of the battery, 100 microns in total.
Dr. McKenzie, you have about 2 minutes.
Great. Another example we work on is example of an interesting materials integration is printed conductive organogels for strain sensors and medical simulations. Problem with medical simulation right now, interesting application for medical devices is your options for training are to work on cadavers or computer simulation. At one end, of course, in cadavers, you get are very expensive and you get no response. Computer simulations, you get a lot of information, but it's virtual. It's not physical contact. We're actually going through the actual mechanisms of a surgical procedure. So we wanted to, working with the device, the CREST lab in the University of Washington Medical School, we developed actually stretchable electronics for medical simulation and that provide feedback. And an example operation is a YV-plasty, where a part of your skin is pulled down and restitched and stretched. It gets stretched a couple 100% during that procedure. And we want to know, are the students or are the doctors practicing for a complex operation, are they doing it properly? Are they stretching enough? Are they stretching too much? We want to sensorize this device. So we develop a 3D printed structure involving different silicones of different to simulate skin, but most importantly, we have to develop a 3D printed organogel that again has that's the actual meat of the sensor that allows flexible sensing. We have to custom engineer that material so we get special flow properties. We want the material to flow when it's printing, and we want it to be solid as it sits there so that the feature doesn't slump, but also so that we can print other materials on top of it, simulate additional layer skins on top of the organogel without it losing its physical shape. And so we do a lot of rheology engineering on those inks, in addition to the electrochemical properties, and can produce gel-like and viscous flow regimes in a printable material for a sensor. And here's a kind of example of an actually fully integrated 3D printed sensor where we're actually, and you can see on the right, we're actually looking at the electrical response as we stretch these different skin flaps during this operation, the stitching operation. We get direct feedback. So we can actually have something that's mechanically similar to human tissue, but gives us sensorized feedback to give feedback, training feedback, and practice feedback for the device. We've actually shown this sensor to be quite reproducible over many thousand cycles, strain cycles, using these sort of printed, rheologically engineered organogels, 3D printed organogels from our Inscript system, with very close tracking, direct tracking of input signal and sensing signal, and a very high reproducibility. I'd just like to close to say that this fits into a larger part of our lab, which is an open access industrial laboratory. We provide access to the Inscript tools along with all other print tools, characterization tools, and professional staff for people to do research across scales, from prototyping, Inscript style prototyping and small scale manufacturing, all the way through to very large scale solar manufacturing and even grid integration studies. So with that, I think I'll wrap up.
Thank you very much, Dr. McKenzie. Thanks for that presentation. LJ is going to introduce our next speaker.
So great talk so far. Just a reminder to our audience, feel free to use the Q&A tab down there at the bottom to ask some questions. After our last speaker, we'll get to those questions. So our last speaker today is Dr. Raymond Tipper-Rumpf from the University of Texas, El Paso, where he's a professor of electrical and computer engineering. He's also the founder and director of the EM lab there at UTEP. Dr. Rumpf's a fellow of SPIE and a senior member of IEEE. Dr. Rumpf and his team are really global leaders in the automation of hybrid 3D printing, as he calls it, of multi-material parts. And as Mark talked to us about earlier, some of Raymond Rumpf's work in software in this area is definitely world leading. So it's my pleasure to introduce my friend, Dr. Raymond Rumpf.
Thank you, LJ. Can everybody hear me?
Yep.
Okay, you can hear me. Great. So thank you, Inscript, for inviting me and for doing these webinars. This is a great resource for everybody. So yeah, title of my talk, Hybrid 3D Printing of Volumetric Metal Dielectric Structures. And interestingly, my group did not start off being a 3D printing group. We were interested in doing electrical things with 3D printing and thinking about what that would enable. And after a few years, we got a bunch of crazy ideas together, and we focus on the disruptive, revolutionary ideas. And we realized that there's not a lab in the world that can build some of the things that we had in mind. And so I don't know where this was, 2014, 2015. And so we had to dive in the deep end of hybrid 3D printing and learn how to do this. And what we wanted to do, what all these crazy ideas had in common, is this arbitrary distribution of metals and dielectrics throughout 3 dimensions. And so
Hey, Tip, you're not sharing, just so you know.
Oh, crud. Well, that's embarrassing. Let me share screen. Okay, is that good?
Good to go, man.
All right. I don't know how I messed that up. Okay, so our lab, we started off focusing on just how to use 3D printing, what new can it do? And so we found ourselves not able to make some of the ideas we had in mind. So we had to dive in the deep end of 3D printing and develop for ourselves the ability to build 3D structures that have an arbitrary distribution of metals and dielectrics. And so in this talk, I'm going to focus on that technology and not so much on the different electromagnetic things that we have done, but we've worked across the frequency spectrum from DC up to optical frequencies. So I think a great topic to talk through is our work in 3D volumetric circuits, and this is really what drove a lot of our innovations here. So if we think of circuits, we think of roads on a map. And if we pop open our computers and we look at the circuit boards, everything is quite flat. And so we have in mind doing something that's much more 3-dimensional, where the components can be placed at any position X, Y, Z, can be oriented at any angle theta and phi, and the interconnects can follow these smooth sort of splines throughout 3 dimensions. And if that could be done, that would allow a much more intelligent placement of the components, which would minimize your size, would minimize your weight. It would reduce the lengths of the transmission lines, which then improves power efficiency, increases bandwidth. If we can avoid sharp bends and vias, we're reducing parasitic impedances to improve bandwidth and performance. And in 3 dimensions, there's just physics that exists that does not exist in 2 dimensions. So there's a lot of reasons that we wanted to go 3-dimensional. And so this drove a lot of work. The first thing we realized, like Dr. Boroznik mentioned, there's no tools or software for doing this sort of thing. So here's the process that we eventually came up with. So we started with schematic capture. We didn't invent anything there. We used a program called DipTrace, and there's nothing special about that. We could have used a lot of different packages that happened to be free to us, and it exported all of the component geometries and the net list and the things that we needed. So the first thing we had to do was develop a tool to lay out the components and route interconnects in 3 dimensions. And so we went with an open source software package called Blender, which has a Python interface that we can script. And that imported all of the component geometries in the net list and allowed us to design 3D circuits, true 3D circuits. And so on the left, you're looking at a very high speed movie of laying out a circuit in the shape of a bullet or a missile. But step 1 for us is laying out the components. And Blender is actually an artist tool. It's not really a CAD tool, although it can be used for that. And that has actually given us very good use of all 3 dimensions, whereas like Pro-E and SolidWorks, technically we have access to all 3 dimensions, but even those tools limit you to planes. We're always sketching on a plane, extruding, and it's rather Cartesian, whereas an artist tool, you have infinite freedom. So step 1's laying out the components. Step 2 then is routing all the interconnects, and then it exports that as a CAD file. And this is sort of where we were stuck. How do we build that? And so we had to develop our own processes and our own software to do that as well. And so basically it works like this. We have essentially 2 CAD files. One is the plastics, one is the metals. And of course, we can extend that to even more materials. And we join that into a single model. And we import that into a slicer. And in fact, all of these processes and slicing algorithms that we've developed, we're working on commercializing that in a product that we call OmniFab. But we can do hybrid slicing, and where each of the paths is controlled with a different technology. So our metals, for example, put down by micro dispensing. The plastics are put down by fuse deposition. We can also come in with CNC machining or other types of tools, and we can mix all of this. And so we've developed a slicer which can do all of that and a lot more for us. And so given that, it generates a G-code file, which then drives the printer. And we're looking on the right is our very first 3D volumetric circuit at various stages of the print that we interrupted it. On the left, you're looking at a movie of that. And then once in a while, you can see the tool changes from the plastic to the metals that it's printing. And so summer 2018 is, we had been working for many years actually, and it finally all came together, and we worked all summer on this, and we got a wonderful circuit working. It was a huge breakthrough for us, but I'm kind of a jerk, and I told my students I hate it. And that's because it didn't look very 3-dimensional. It was very square. It just looked like a thick circuit board to me. Yeah, even though internally it is volumetric. So they chuckled at that. They tolerated me. And so the next thing we did was lay out something that was not supposed to look like anything, although it looked kind of like a bean. We put a hole through it just to do that. And so we end up calling this effectively the Hole Free-Hole. And so that kind of put an end to our developing a process to make these 3D volumetric circuits. And fortunately, I'm limited in time, but we're doing some other things now. We're doing some RF radios, and we're doing some other volumetric things that aren't necessarily circuits, but antennas, metamaterials, bandgap materials, that sort of thing. So that is our Hole Free-Hole. So our OmniFab tool, we had some problems with long duration prints, and there was a lot of fixes to that, but some of what we added is maintenance of the tools. So as we switch the tools, we can take the tool off to the side, we can scrub it, you can see the brush sitting there. We can dispense ink or some of the plastic to clean the heads between the prints. And that, a combination of a variety of other things, lets us extend our prints to multiple days, we hope. And on the right, it's actually the first block that we have ever printed with our own custom slicer written from the ground up. And actually, even before that, some of the other things we've done with our slicer, we were doing off-axis printing. You'll see a lot of people spending a lot of money for 6-axis robot arms for doing off-axis printing. And in fact, we can do a lot just with a standard 3-axis printer. That's a 3-axis cheap little maker bot. And we also did conformal printing with that same printer. And here's we call it the puck, but it's a UTEP logo. And you can see that the base was actually printed off-axis, and the pickaxe logo on top was printed conformally. So we kind of have this, I don't know, we have this saying that the 1980s called, they want their slicers back. It's time for a new modern slicer that can do all of these things. And we don't necessarily need big, expensive printers to do advanced things. We can do that just with a new slicer. So just before I end, just some other volumetric things that we're working on. One is our frequency selected surfaces. And this is just a flat panel that when electromagnetic waves try to pass through this, some frequencies get through and some reflect. And so it's frequency selective. And what we're looking at now is transmission. So this is designed to reflect a narrow band of frequency. So we're seeing a dip in transmission. So that is a frequency selective surface. However, there's a desire to put these onto curved surfaces. That could be a wing of a UAV, that could be a radome of an antenna. And it's not really known how to do this. And so what people do is they project the pattern down or other types of mapping techniques. But what that does is it deforms a lot of the elements. At the top, the elements look pretty good, but the elements on the side have been stretched because they've been projected, and these no longer work anymore. And so we have a neat algorithm, actually, we call spatially variant lattices. We're doing a lot of other stuff with that. But one thing we can do is actually come up with a better distribution of elements across curves. And so we can actually bend and twist periodic structures, but still maintain the size and shape of all the unit cells. And so that actually maintains the electromagnetic properties. And so this next slide actually, I think, shows this a little bit better. On the left is a conventional frequency selected surface, and it is not selecting frequencies. And on the right is our spatially varied version, and is doing a very good job of blocking a particular frequency and reflecting that band. And so, of course, this is all enabled by digital manufacturing as well. We're doing some antenna work. One of the electromagnetic mechanisms that I haven't really talked about, but it's making the dielectrics artificially anisotropic. And that actually lets the plastics do functions for us. Most electromagnetic people just think of the plastics as a way of holding the metals in place, and the metals doing the function. But we can actually make the plastic do profound functions. And so we're looking at incorporating these types of degrees of freedom, these new degrees of freedom that we've identified, and incorporate them into 3D antennas and hopefully approach fundamental limits. And so this is a pretty well-known antenna. It's called a compact ultra-wideband antenna. This was designed by Virginia Tech. And you can see an X-ray scan on the lower left of our 3D printed version. And there's a few little breaks in this. It wasn't working, and well, we figured out why. So I guess we stopped dispensing over a certain part of that. So that's another volumetric part. You can also imagine metamaterials and bandgap materials. We're spatially varying those. We're printing those across curves and other things. And that all requires this ability to build volumetric parts with an arbitrary distribution of metals and dielectrics. So that's it for my talk. I focused exclusively on the hybrid printing and not so much in the electromagnetic mechanisms, but I would love to answer questions. I could talk forever on that.
Thanks a lot, Dr. Rumpf. Really appreciate it. And we're on schedule, so I really appreciate that too. We're going to get some questions from our audience, and I'm going to switch it over to Brendan, who's going to monitor that for us.
Thanks, LJ, and thank you to all of our speakers today. You guys did wonderful, and we're really excited to see how you guys are going to change the future of additive manufacturing with printed electronics and hybrid electronics, antennas, and just everything else with that future. So our first question We'll go to Dr. Jing Wang, and it is, how about fabrication of dielectric photonic band gap structure?
That's actually a very good question. So the dielectric waveguide we developed relies on the total internal reflection. We have almost like a band gap-like reflection feature at the boundary between the high K and low K structures. Particularly, Dr. Weller and another colleague of mine also working with optical fiber-like print. They have some initial work. Just because of lack of time, I did not able to present that part. But some kind of band gaps engineering structure will require you to have a drastically different dielectric constant. So long you can engineer those material as a feedstock, you can print them with a good enough finishing geometry control and qualities. You could implement filter, splitter of the power and other structure which we explored. Because I'm not showing the slides in the in the slideshow mode. There are some movies at the end of my presentation shows how you can direct the wave into the different features using something almost similar to the band gap concept or the lens concept.
Thank you, Dr. Wang. We appreciate that answer. It looks like we only have one other question. This is from Justin Nussbaum. He says, this is fascinating work, and I really appreciate you all sharing this with us. As a general question to any speaker who would like to answer, how do you see these capabilities evolving from important academic R&D to end use applications, and how far are you from these applications? Thanks for sharing. So since we have plenty of time, we could give you guys about 3 to 5 minutes to answer, and we could just go through the line of your guys' answers. Dr. Wang, since you're already answering the previous question, would you like to take a hit at this one?
Sorry, can you repeat the question?
Yeah. So his question is, as a general question to any speaker who would like to answer, how do you see these capabilities evolving from important academic R&D to end use applications, and how far are you away from these applications? Thanks.
The answer is it depends on the progression of all the material development, all the printing modularity process, integration development. So far, most of the system presented here looks like a lot of us are exploring to use a single platform to do a lot of things. Polishing, laser, machining, printing a metallic structure, dielectric structure, control the dielectric constant by playing with composite materials. That can take care of a lot of this initial design and prototyping and getting the best performance part. The next layer of the question is how you can get to the yield, productivity, the volume, and also how can you get to the repeatability question. Let's say you want to do a phase array on a conformal surface, you could well get it done after a long journey, but otherwise in other technology, you just cannot do it. In those kind of process for low and mid volume, I can already see there's almost not a huge gap from academic research to some level of mid and low level production, which require a lot of customization, a lot of integration, which is not easy to do or impossible to be done using traditional multi-layer board. And you can take care of the 3D geometry, having a conformal curved, doubly curved structure. And you can also take advantage of spatially changed material properties, leveraging both dielectric, ferrite, piezo, either piezoelectric or piezoresistive, as well as a battery, which is fascinating work. Then you can print the entire system without going to different tooling and different system, but still had peak performance that you can otherwise not able to achieve. But to go to the very large volume, in a very simple product, think about a stir pan. The traditional manufacturing technique may still be the best. It is something that needs a customization, high-level integration, challenging incompatible processes that you can put together in an additive platform, potentially a single platform that can have a huge leadway into the future development. That is just my point of view.
Thank you, Dr. Wang. Dr. McKenzie, you actually had some good insight as well on the Q&A section. Do you want to just go over what you had answered before?
Yeah, I was. I think there's a broad range. Of course, things in the medical side, in terms of when will these technologies sort of reach the market. Naturally, in the medical side, part of our strategy is to address the regulatory issue. To get something approved through FDA and all that takes a significant amount of time. To get things improved for implant devices, which ultimately we talk about 3D printing organs, 3D printing tissue, but that's pretty far out. One of the goals of actually doing that medical simulation is a way to get that into a useful product now, because as a training device, it doesn't have to meet the same regulatory requirements. So there's a full spectrum of very long-term stuff that will, is 10 years out, to stuff like some of the sensors and even some of the other applications I didn't have a chance to talk about, things like thermal management material structures or high density interconnect type stuff that is actually very close. It's just it's finding that right business case and not so much the technology case at this point. So there's really a full spectrum of stuff that's very close to meeting in applications and other stuff that's further out. And we actually try to bridge that gap with examples like the medical simulation, where it is a medical sensing device, but it doesn't have to be FDA approved because it's not actually going in the body, but it's a stepping stone device to flexible electronics on the human body.
Excellent. Thank you, Dr. McKenzie. So you guys all, excuse me, you guys all had very great results, and all of your studies, your work, the progress that you guys are making is just incredible. I guess this is just another question to all of you. Will the direct digital approach be an issue because of the speed? And then we can use Dr. Rump to answer this question.
So definitely in the short term, I think 3D printing is going to follow a Moore's law. I also think it's going to sort of change the paradigm of how this is done. Like right now you have Foxconn that turns out, I don't know, 1 billion cell phones, but they're all the same. Suppose I ask Foxconn, I want those 1 billion cell phones, but I want each one to look a little bit different. Oh, they can't do that at all. The other thing, rather than have one company churning out a billion cell phones, I think you'll see thousands of small businesses turning out just thousands of products. Maybe someday you'll take a vacation to Jamaica and they're making, I don't know, cell phones in the shape of palm trees that day. And so you get that, and that's your souvenir, it's your cell phone for the next year. I think you'll see a lot of stuff like that. Cell phones is probably a little bit farther off, but you can imagine they're already printing jewelry. So I think it's going to shift from the big manufacturers to small businesses.
I appreciate that. That is very good insight. Thank you. We have another question. I know there's a lot to tackle to bring 3D printed electronics to end use, and it's great to hear how you've solved many of these issues already. Oh, I'm sorry. Excuse me. The next question is, where do you see most of the innovation happening in microwave design? We could let Dr. Mark answer this.
Am I muted or I'm good?
You're good to go.
Okay, great. So I think we showed some of the areas where I think it has the most impact. It really is areas that require either complex geometries, unusual material properties, spatially varying material properties, or 3D integration. And I think as, it's got to the point where the technology that we can make has kind of got ahead of the theoretical developments, right? There is really very little you'll find on how you would optimize, for example, a transmission line if you had the ability or antenna to vary the substrate permittivity randomly or arbitrarily, right? People didn't investigate it much because it was impossible to fabricate. And now we can fabricate those things, and I think as time goes on, we'll develop ways of designing really optimal structures that meet fundamental limits in performance. So I really think it's these really high performance applications down the road that this is going to make a big impact on.
Appreciate the answer. Thank you, Dr. Maratsnik. Dr. Rumpf, do you have anything to add to that?
I would just add, I think a lot of electromagnetics is primarily flat right now, and that it was due mostly to how things were manufactured. We make most things out of printed circuit boards. So I think 3D printing will open up the third dimension. There's a lot of benefits to the third dimension. There's a whole degree of freedom. There's physics that exists in 3 dimensions that does not exist in 2 dimensions. for example, anisotropy. Very hard to exploit that in a two-dimensional setting. So I just think there's a lot more degrees of freedom in that third dimension, and I think that's what will change microwave designs going forward.
Thank you, Dr. Rumpf. That is all the questions we have for the Q&A section. I believe, oh no, we have another one, I'm sorry. The question is, do you think it will be difficult to convince people in microwaves to jump on the 3D printing bandwagon as it was for microwave people to jump on the MEMS bandwagon, especially for high power applications? And you can answer that too again, Dr. Rumpf.
Sure. I think one big mistake we're making that's stopping a lot of people from jumping on the bandwagon is we're 3D printing stuff that already exists with very, very mature technology. And so it does not perform as well. And so we're not very convincing that way. I think we have to figure out what 3D printing can do better and do that, because those will outperform the standard flat stuff that people are doing. And I think that's what will make them join the bandwagon, when the stuff just works better and shows clear benefits.
Thank you. So our next question is, many mentioned materials. Do you think we must match state of the art in performance before we can compete with working devices? Mr. or Dr. McKenzie, you can answer this one.
Sorry, could you, I didn't quite catch that.
Sure. So many mentioned materials. Do you think we must match state of the art in performance before we compete with working devices?
I mean, that's a great question. In some spaces, you know, in the large scale, low cost world, large format stuff, yes, and solar, yes. In some of these cases, there is no competing product in these sort of integrated, say, stretchable electronics and things like that. So, you know, you kind of got greenfield advantage. So I think there's a range. I think there are cases where any ability to provide stretchability or things like that in on-body applications, any a battery, say, for example, the thin battery case, a lot of these applications are no longer constrained in the XY direction. We work with an organization called NextFlex, you may have heard, and we worked a lot on figuring out the power systems. And actually, initially, everyone comes in, I need a bigger battery. Battery doesn't have enough capacity. Actually, we looked at a lot of those applications. It turns out that's not the problem, because you have a lot of surface area. So for example, in the battery space, you don't exactly need to compete on capacity to a lithium battery, but you can provide these other features, conformability, the toxicity, the transportation issue. So it varies from application to application, but there are definitely applications where you're not really competing on some of the conventional specifications, and you're providing a feature that there really is no competition for. And those are, of course, the best applications. So.
Thank you, Dr. McKenzie. I would like to direct that same question to Dr. Mraznik.
Sure. So I think in some cases the answer is yes. That, for example, we're trying to do some very high frequency RF devices, and the printable conductive inks these days are simply too lossy to be able to make those things compete with conventional manufacturing. So that is limiting our ability to go up to higher and higher frequencies. And there are application spaces, though, that we're looking at where there are no competing technologies. So it's better than not being able to make it at all. But it certainly would benefit the field to have better materials.
So I just wanted to thank all of you guys. You guys are all pioneers and disruptive, and this means you will have many haters. But on behalf of NScript, we're in love with you guys and the work that you guys do. I'd like to just send this back to John and LJ to wrap this up. Thank you, guys.
Yeah, thanks a lot, Brandon, for all your work too. And thanks for the folks that spoke with us today. I really appreciate you all. As Brandon just said, you're doing awesome work. I'm really excited about it. And to the audience members out there, thanks for joining us. John?
Yes, thanks to all the speakers. Great presentations, great work that you're doing. And I just wanted to remind everyone about part 2 of this webinar, which will be Tuesday, July 7th at 1 p.m. Eastern.
Correct.
Thanks, everyone.
Have a good one.
Thank you. Thank you. Take care. Bye now.